Okay, so today we're going to show you guys how to do mathematical induction. So in the cases that you're going to do mathematical induction, you'll be given a problem that would say prove that something is true for a certain amount of cases. So that would be written more simply as prove that P of n, that's whatever you're trying to prove, is true for all cases where n is greater than j. So j would be some type of number. Sometimes it'll say where n is greater than or equal to 1, but sometimes it's some other number, as we'll show you in some examples. So what you're going to do for mathematical induction, the first thing you're always going to do is your basic step or your base case. So that is you're going to take whatever the minimum is, so whatever j is equal to, so if it says n is greater than or equal to 1, then you would do 1. If it's n is greater than or equal to 20, you would do 20. So then you're going to show that p of whatever that number is true. Right? So, for example, if p of n is n plus 1 or something, then you would say, and say j is 5. Then you would just say p of 5 is equal to 5 plus 1 equals 6. Okay? So then, for your inductive step, you would do your inductive hypothesis. So your inductive hypothesis is going to be that you're going to assume that P of k is true for all cases where n is greater than or equal to j. So basically you're just assuming that what was given to you is true. And then where the real problem comes in is when you're going to do your inductive step, and that's where you're going to show that P of k plus 1 is true. So k plus 1, so that's just going to show that no matter what number you're doing, plus 1 is always going to work. So you're just going to do k plus 1. Instead of using actual numbers, you would use k plus 1 to prove that whatever you're trying to prove is always going to be true. So we're going to do some examples which will make it a lot easier to understand.
Okay, so now we're going to look at a numerical example. So what we are going to prove is that we're going to take the sum of all integers starting from 1, and we'll take this sum up to an arbitrary integer n. We're going to say that this is equal to the following. So the sum of all integers, consecutive integers, 1, 2, 3, all the way to n, is equal to n plus 1 times n over 2. And so to do this proof, we're going to first start out with our base case. And let's call this function p of n. So we're going to start with p of 1. So obviously, the sum of all, consecutive integers, positive integers up to 1 is going to be 1, right? So we want to see if this formula holds true. So since we have n being 1, we have 1 plus 1 times 1 over 2 equals 2 over 2, which is 1. So our base case works out nicely. And now, so our next step is the inductive hypothesis. So we're going to assume that the sum of all positive consecutive integers up to k is going to be equal to k plus 1 times k over 2. And assuming that this is true, we are going to show that p of k plus 1 is also true. So now, since we know that p of k is k plus 1 times k over 2, we already have this sum. And since p of k plus 1 is just equal to p of k plus k plus 1, right? So since p of k I already have written out right here, I can just add a k plus 1 to that. And so that would get me p of k plus 1. Let me erase some of this so we have more space. Alright, so now we're going to do a little bit of math here. We're going to find a common denominator. So we have our p of k, and then we're going to convert the k plus 1 to having a 2 in the denominator. So we multiply the top and bottom by 2. And so now, this will be equal to k plus 1 times k plus 2 all over 2. Because here we see that there's a k plus 1 term right there and a k plus 1 term right there. So we factored those out. And so now, so now we just have k plus 1 times k plus 2. And now we see that this is equal to p of k plus 1, because if we substitute k plus 1 in for n in our original formula, we would get the same thing, because k plus 1 times k plus 1 over 2 is what we have right there. So therefore, the sum of all positive consecutive integers from 1 to n is equal to n plus 1 times n over 2. And that's proved by regular mathematical induction.
Okay, so now we're going to do another example of induction. So for this example, we have 5 or 8 piece chicken nuggets, and we want to prove that you can make any number after 28 with a combination of those 5 and 8 piece chicken nuggets. So what we're going to do first, obviously, is do our base case. So our base case, we're going to obviously start with 28. So p of 28 is going to equal. So now we want to think about how we can get the number 28 using 5 and 8 piece chicken nuggets. So since there's an 8, it's probably obvious that we can do 5 times 4 and get 20, and then add 1 times 8. So this is going to be 20 plus 8, which is going to give us our 28. Okay, so that's our base case. So usually with your base case, you want to just start with, in this example, it says any number after 28, and including 28. This one also includes 28. So since it includes 28, you want to usually start with whatever the lowest number is. So 28 is our lowest number for our cases, so that's why we started with 28. So now we're going to do our inductive hypothesis. So for our inductive hypothesis, we're going to assume p of k is true for k is greater than or equal to 28. So for your inductive hypothesis, you always want to assume that p of k is true, because in your inductive step, you're going to show why p of k plus 1 is true. So first you'll assume that p of k is true, and since it's given that we want greater than or equal to 28, we want k to be greater than or equal to 28 in our hypothesis. So then for our inductive step, like I just said, what you're going to do is you want to prove that p of k plus 1 is true. So, how we're going to do that is, since we started with 28, so we're going to say, how would we get from 28 to 29? So, if we look at how we would get 29, you would do 1 times 5 plus 3 times 8. So you do 1 5-piece and 3 8-pieces. So this is because 3 8-pieces is 24 and 1 5-piece is 5, so you're going to get 29. So let's do 32 so we can just look at Doing these examples just kind of helps you get a feel for like what's going on in the problem. So 30 is an easy one, 6 5 pieces. And 31, 3 times 5 plus 2 times 8. So I'm doing this. This isn't part of our inductive step, so it's not really part of the proof, but it's just so that we can get a feel for the problem, so we understand what's going on. So this one we're going to do 4 times 8 for 32. So if you realize there's actually a pattern emerging. So for that pattern, we're going to look at what we did to go from 28 to 29. So to go from 28 to 29, we noticed our 28 had 4 5 pieces, and now it has 1 5 piece. So what we did is we subtracted 3 5 pieces, and we added, because we went from 1 8 piece to 3 8 pieces, so we added 2 8 pieces. Now this works because we have 3 5 pieces is 15 and 2 8 pieces is 16. So this ultimately ends up in a plus 1. So that's how we add 1. So if 28 was our k and 29 was our k plus 1, we realize that we added 1. So that's how it's the k plus 1. But now look, for 29 to 30, we couldn't do that because we didn't have 3 5 pieces to take away. Instead, we just subtracted 3 8 pieces and added 5 5 pieces. Now this works because 3 8 pieces is 24 and 5 5 pieces is 25, so it ends up ultimately with a plus 1 as well. Now if we look, when we go from 30 to 31, there's enough to subtract 3 5 pieces, which is our first case, that's this one, because there was 3 5 pieces, so from 30 to 31 we could subtract 3 5 pieces and add 2 8 pieces. So you can notice that no matter what, for any number after 28, we're going to have at least 3 5 pieces or at least 3 8 pieces. So since that works, we have proven that no matter what k is, we can always subtract 3 5 pieces or subtract 3 8 pieces, and we can add the 2 8 pieces or the 5 5 pieces to get k plus 1.